Okay, our first talk today will be by David Keating from University of Wisconsin. And David will talk about k-tilings of the Aztec diamond.
Thank you. I'd like to thank the organizers and Filippo for inviting me. And like Sasha said, I'm going to talk about k-tilings of the Aztec diamond. So the outline of the talk. So Sylvie gave a nice talk on Thursday on a review of interlacing partitions and how these are related to tilings. So since there are some new people here today, I'm gonna also do a short review of interlacing partitions and how they relate to Aztec diamond. So we'll focus on the stuff that'll be relevant for us.
Could you please make your microphone?
Is that better? Okay, so we'll use some sequences of interlacing partitions to construct, or there'll be a bijection between sequences of interlacing partitions and domino tilings of the Aztec diamond. And there will also be a bijection between these sequences of partitions and a certain vertex model. So this will give us a way to relate the vertex model with tilings of the Aztec diamond. And in the vertex model formulation, we'll have some integrability. It'll be Yang-Baxter integrable. And we'll use this to compute the partition function. So we'll use this to count the number of tilings of the Aztec diamond. So we'll spend quite a bit of time on just this basic stuff that probably a lot of people know. But it will be useful for us because when we introduce the k-tilings, everything will work more or less exactly the same, except for our vertex model will be slightly more complex. Then after we introduce the k-tilings, we'll compute their partition function, and then we'll state some combinatorial results we were able to prove. So this was joint work with Sylvie and her student, Andrew Gittman. So first off, some review of interlacing partitions and tilings of the Aztec diamond. So what will be useful for us? We'll need to know what partitions are. There'll be sequences of non-negative integers where lambda1 is bigger than lambda2 is bigger than lambda m. We'll say the size of a partition is the sum of all its parts. So for this example here, we have lambda equals 322. And we'll often think of this in terms of its Ferris diagram, where we take the largest part and we put it on the bottom. That gives us a row of 3 cells. And then the second largest part gives us a row of 2 cells, and then another row of 2 cells. And we'll think of the size of the partition as just the number of cells in this diagram, or just the sum of the parts. So this is 7. We'll also need to know the conjugate of a partition. So to conjugate a partition, we're just gonna, instead of reading along rows, we're gonna read along columns. So the conjugate of 322 is gonna be 331. So drawn here. And the size is going to be the same. Okay. We say that 2 partitions interlace if their parts satisfy this interlacing condition. It's sort of easier to see in the diagram. 2,2 and 3,2,2 interlace because the cells that we have to add to the diagram for 2,2 to get 3,2,2, you don't add more than 1 cell in each column. So here we only add a single cell in each column. So these interlace. It's equivalent to this condition up here. And we'll say that partitions co-interlace and use this symbol if their conjugates interlace. So equivalently in terms of the diagram, if you don't add more than 1 cell in each row. For the most part though, we will be thinking about partitions in terms of their Maya diagrams. So to construct the Maya diagram of a partition, we start with its shape, we draw its diagram, and then to every horizontal step, we're gonna put a hole, and on every vertical step, we're gonna go to particle. And then we're gonna read the sequence of holes and particles, starting up here at positive y-axis infinity, and going down along the shape of our diagram, and then off to x goes to infinity. So this will give us some sequence of particles where to the left, we have infinitely many particles, and to the right, we'll have infinitely many holes. And as Sylvie mentioned in her talk, there's a unique center, which I've drawn in a red line here and the red line here, where the number of particles to the right of this line is equal to the number of holes to the left. So even though these are an infinite sequence of particles and holes, there's a unique way to center them, which I will often indicate by a red line. All right, so that's the basic information we'll need about partitions. And now let's talk about the Aztec diamond. So this was introduced in the 90s. It's a region of the checkerboard where you cover a tiling of it by dominoes is where you cover adjacent squares by these 2x1 dominoes, either horizontally or vertically. So the rank of the Aztec diamond is a number of corners along any of the edges. So here is a rank 3 Aztec diamond and one of the possible tilings. Okay, so it's well known that if you take the rank to be very large and look at, say, one domino tiling uniformly chosen from all possible domino tilings, it exhibits a limit-shaped phenomenon where we have some disordered region in the center and some frozen regions in the corner and some Arctic curve separating the disorder from the frozen regions. And in this case, the curve is known to be a circle. So we'll say more about this when we talk about k-tilings later. Okay, so now we want to construct a bijection between these tilings and interlacing sequences of partitions. So to do so, we're going to assign particles and holes to the faces of our checkerboard according to these rules. So whenever you see a vertical domino where the white square is on top, you're going to fill it with 2 particles. And if the white square is on bottom, it gets filled with 2 holes. And there's a similar rule for the horizontal dominoes. So for the tiling where every domino is horizontal, this is what you get. Here I'm only drawing the particles and I'm leaving out the holes. So wherever there's not a particle drawn, you should just think of a hole being there. And for this tiling, this is the holes and particles that you see. So now we're going to think of these particles and holes as living on the diagonals of our Aztec diamond. And we're going to think of them as being along each diagonal, the Maya diagram of some partition. So you should imagine that down and to the left, it's just fully packed with particles, and up and to the right, it's fully packed with holes. And so along each slice, you can read off the Maya diagram of a partition, where the unique center of the partition, it like kind of shifts along the slice. So I've drawn this red line here to indicate where the center of the partition will be. So for, and so in fact, the domino tiling is equivalent. There's a bijection between these sequences of partitions that interlace in this fashion, where you start at the empty partition and then you co-interlace and grow bigger, then you interlace and grow smaller, and then co-interlace and grow bigger, and so on and so forth until you end at the empty partition again. The sequence of partitions you get using this rule, in fact, are exactly these. So in this case here, our sequence of partitions is just all empty. So this is sort of the minimal configuration. And in this case, we get the following sequence. So we started empty, and now we look at the next slice, and we see that these particles have each like moved up 1. So we see we have the partition 1, 1, and so on and so forth. You can read off each partition along each slice. So this gives us a bijection between the domino tilings and sequences of interlacing partitions of this form. Okay, so we're going to assign some weights to them, so we don't have to stick to the uniform tiling. We can bias the vertical dominoes. So there are 2 types of vertical dominoes, and we're going to give them different weights. So for this type of vertical domino, we're going to assign an xi, where I tells you what diagonal slice this vertical domino is living on. So for example, here we see such a vertical domino, and the white square is on the diagonal numbered 3. So it gets an x2, since 3 is 2 times 2 minus 1. And this x2 is one of, or I guess the only x2 that appears in the weight of the tiling. And this vertical domino has the white square on bottom, so it's going to get a y. And in this case, the white square is on diagonal 5, so it's going to get a y3. And there's another vertical domino that will get another y3, so we'll get a y3 squared in the weight of the tiling. And our goal will be to compute the partition function of the Aztec diamond with these weights. Okay, before we get to the vertex model, I just want to say that these weights in terms of the sequence of partitions, well, that they have a nice meaning in terms of just the sequences of partitions. So here we had this sequence, and the weight of x1 is just the number of boxes you need to add to go from the empty partition to the partition 1, 1 in terms of the diagram. So in that case, you need to add 2 boxes, so we get an x1 squared. So yeah, these x and y weights sort of tell you how much you grow or decay at every step in this sequence of partitions. And if you're familiar with like symmetric polynomials, you can actually write this weight in terms of a product of Schur polynomials. So in fact, these domino tilings are just an example of a Schur process. And these Yang-Baxter relations I'm going to use later to simplify the partition function and to compute the partition function. In terms of symmetric polynomials, are kind of equivalent to using the Cauchy identity to simplify things this way. So if you're familiar with the symmetric polynomials, there's some way to rewrite all of this in terms of symmetric polynomials. Okay, so now we're going to go to the vertex model formulation. So we're going to be looking at vertex model, like path configurations of this form. Well, we'll have some sort of upright paths that start at the bottom and end at certain places on the side. And these different colors here, like the purple and the gray, are just going to indicate like the different weights we choose in each row. Each row is going to have a different choice of weights, and we're going to indicate that by color. And by choosing these different weights, we're going to impose different allowed configurations along each row. And so what we'll end up doing is that the positions where these paths cross a horizontal slice, that's going to be given by a partition. And the weights we choose for these rows are going to impose interlacing conditions on these partitions. And so we'll have a bijection between these sequences of partitions and configurations like this. And it turns out the weights we've chosen will appear nicely in terms of the vertex weights as well. And then once we have everything in terms of a vertex model, we'll be able to use the Yang-Baxter to simplify this and compute the partition function. Okay, so that's our plan. So I'm going to do it, like I said, in a decent amount of detail, because when we do the k-tilings, it works almost exactly the same. So if you can understand it for the 1 tilings, then that contains most of the ideas. Okay, so we need our weights of our vertex model. So for a purple row, we're going to have a certain 5 vertex model, where you get an x whenever a path exits to the right of the face. Right. So for example, in this single row, we have 1, 2, 3 faces where a path exits to the right. So the weight of this row is x cubed. And one can check, which I don't do here, that the condition on, so to each boundary, we're going to assign particles where the paths enter and exit. And we're going to think of these as being the Maya diagram of some partition. And one can check that with these weights, the rows that have non-zero weight will be the rows in which mu and lambda co-interlace. And then the power of x that you see is exactly the number of boxes you need to add to mu to get the lambda. So in this case, we have to add 3 boxes to get from 2, 0, 0 to 3, 1, 1. And that's exactly the power of X we saw from the pads exiting right. Okay. So just some points. Given the boundary conditions, there's a unique, for a single row, there's a unique way to fill in the pads. And like I said, the weights agree with the weights we assigned to the co-interlacing partitions previously. So these are the purple ones. For the gray weights, it's slightly more complicated. Now we have a different 5 vertex model. We don't allow this cross vertex anymore, but now we allow a horizontal vertex, which wasn't allowed before. And here we're assigning a weight of y to the empty face and the faces where the pads exit at the top. So it turns out, so just again, we're going to assign particles to where the pads enter at the bottom, exit at the top. We'll think of these as the Maya diagram for some partitions. And given a choice, or given lambda and mu, there's a unique way to fill in this row. And this will have non-zero weight only if mu and lambda interlace. So the purple gave us our co-interlacing, the gray is going to give us our interlacing. And it turns out the weight will be exactly the weight we assigned to interlacing partitions before, times some factor that just depends on the number of pads and not on the actual partitions. So eventually we're just going to throw that away and ignore it. All right, so those are our 5 vertex models. Now we have a bijection between pads on this and tilings of the Aztec diamond by going through this sequence of interlacing partitions. So given a tiling, we can assign particles like we did before. This will give us some sequence of interlacing partitions. Now we take that sequence of partitions and we draw their Maya diagrams along the horizontal slices of our vertex model. So we start with empty, and then we'd put 1, 1, and then 1, 1 again, and so on. And because of our choice of weights, this will uniquely determine the pads, so we can draw the pads in, and we can read off the weight. And the weights will agree up to some overall factor that just depends on the rank, and we'll just throw that out. Okay. So why is this nice? Why is this bijection nice? Because now we can use tools from integrability to compute the partition function. So in fact, these 5 vertex models are Yang-Baxter integrable. So the weights satisfy the Yang-Baxter equation. So now we need to introduce a new 5 vertex model, a new set of weights, where if we look at a configuration like this, where we fix the boundary conditions along the outside and sum over all the things that can happen on the inside, the Yang-Baxter equation tells us that the partition function on the left is going to be equal to the partition function on the right. So for this case, our R matrix, which is this yellow one, happens to have these weights. The one that'll be important for us is this 1 over 1 plus xy, where the red path is just going straight down diagonally. Okay, so for example, if we fix the boundary conditions so a path is entering in this corner and exiting at the top, on the left-hand side, there are 2 allowed configurations, this one with a V and then a corner, or this one where you go diagonally, then up. And on the right, there's only a single allowed configuration. It looks like this. And if you calculate the weight on both sides, it's equal. So this is useful because it allows us to swap the order of our rows in our vertex model. So before we had like purple, gray, purple, gray, purple, gray. This will allow us to push all the purple rows to the bottom, I guess all the gray rows to the bottom and all the purple rows to the top. So what we can do is that whenever we see our row, gray row, then a purple row, with some boundary conditions that are given by mu and lambda, we'll insert an empty cross on the left. We'll use the Yang-Baxter equation to push it all the way to the right. And then we'll remove the cross. So when we remove the empty cross, it just gives a weight of 1, so nothing changes. But when we remove the cross with the diagonal, it'll give us a weight of 1 over 1 plus xy. So we can reorder the rows up to some factors coming from the cross weights. So now we start with this sequence of rows where it's all gray, then all purple, and we can repeatedly use the Yang-Baxter equation to reorder the rows into the lattice we wanted. And the Yang-Baxter equation tells us that the partition functions of these will be equal up to these weights that come from removing the crosses. So now this is useful because this thing has only one allowed configuration. It's trivial. You can just read off the weight, and it gives you some overall factor, which ends up being exactly the overall factor that we just ignored earlier. That depends only on the rank and not on the actual. For every configuration, this factor shows up the same. So we're just going to throw that out. And we get that the partition function for the Aztec diamond is given by this nice product formula, where each of these terms came from one of our row swaps going from here to here. And in particular, if we set x and y to 1, we get that the total number of tilings is 2 to the m plus 1 choose 2 for the rank m Aztec diamond. Okay, so any questions about this? Okay. Okay, so now we're going to try to do the exact same thing, except we're going to have k-tilings on this side. For interlacing partitions, we're going to have k-tuples of interlacing partitions. So we'll have a sequence of tuples of partitions. And here we'll have some coupled 5-vertex models. So we'll have, say, k copies of this 5-vertex model, where we draw the paths in different colors, and they interact in some way. But otherwise, the arguments will work more or less exactly the same, just with more complicated weights. Okay, so yeah, now let's talk about k-tilings. All right, so like I said, our tilings go to k-tilings, our sequences of partitions go to sequences of k-tuples of partitions, and our 5-vertex model is going to go to k superimposed copies of the 5-vertex model. So for example, here we have a particular 3-tiling of the Aztec diamond. We can look at the particles along each slice for each color. And this will give us, let's say, along the first slice, it's empty for all 3. And now we look at the second slice, and that'll give us another tuple of partitions. And these will interlace in exactly the same way we had before, where the first entry will, or the first entry of each tuple will interlace, co-interlace and interlace, co-interlace and then interlace. And the same thing for the second and the third and so on. So we'll refer to the tilings as being different colors, and we're going to order the colors from smallest to largest, because the T interaction will depend on the order of the colors. So now let's assign weights to these tilings. We'll have the same vertical domino weights as we had before. So we'll have the same bias between vertical and horizontal, but we're going to add an interaction term to the different tilings. So now, whenever we have a pair of colors A less than B, we're going to say that we get an interaction that gives a power of T if, when you superimpose the tilings, the configurations locally, you get a configuration that looks like this. Where here, blue is the smaller color and red is the larger color. So for example, in this 3-tiling, if we look at this blue domino and this red domino, if you superimpose these two, you'll get these 2 dominoes will look like this. And so that'll contribute a factor of T. So it turns out there ends up being 4 factors of T coming from interactions between blue and red. Now, if we look at this blue domino and this green domino, I don't know if you can see the highlighting, but it's supposed to be highlighted. If you superimpose these 2 tilings, you'll have that these dominoes look like this, and this will also contribute a factor of T. So this will be an interaction between the blue and the green. And then this red domino and this green domino give an interaction of the form like this. So if you go through and count them all, for this example, there ends up being 11 interactions, plus the normal X and Y weights coming from the vertical dominoes, just like before. Okay. And just as an aside, the single tiling we talked about earlier was an example of a Schur process. So for these k-tilings, the weights we've chosen end up, you can write them as a product of LLT polynomials with some overall power of t in the front. So these can be thought of maybe as like some sort of LLT process, some generalization of the Schur process. All right, so before we try to count the number of tilings, compute the partition function, I wanted to show some simulations to kind of advertise that these have some interesting behavior. So here is a 2-tiling of the rank 64 Aztec diamond with t equals 1. So when t is equal to 1, there is no interaction. So you see kind of what you'd expect. It looks like 2 circles. The Arctic curve looks like 2 circles. If you increase the rank to 256 and keep t is equal to 1, it becomes more apparent that you're seeing some limit shape phenomenon. But now, if you allow t to, if you change t off of 1, so here t is 0.2, we see that the limit shape starts to change. It's no longer a circle, and maybe we have some sort of cusps forming along this top boundary. And also, maybe surprisingly, that both tilings kind of look the same, even though our interaction weight was not symmetric with respect to the colors. So this is something we don't understand, why we see this like asymptotic symmetry. So here's t equals 5. And again, now we see we maybe have like some sort of cusp forming at the bottom boundary. And if you look, this tiling when t is equal to 0.2, and this tiling when t is equal to 5, kind of look the same up to a reflection. And this is something we can prove combinatorially. And if you look closely near, so here I'm zooming in on this bottom boundary, you get configurations that look like this. So you have the normal frozen region, a disordered region, and then here some sort of like zigzag frozen region is appearing. So this is still for a 2-tiling. And if instead you do a 3-tiling, so the same t weight, but now a 3-tiling rather than a 2-tiling, the frozen region that was in this bottom corner has shrunk a ton. And now maybe we see 2 cusps. I don't know, but there's some interesting limit shape behavior, it seems, for these tilings. So that's something that would be interesting to understand. And here, I guess, is t equals 0. And now we get this egg-shaped limit shape. So we can compute the Arctic curve for t is equal to 0, but for these intermediate ranges of t's, we don't really know what to do. Yeah. Yeah, it still looks like exactly the same. Mm-hmm. Okay, so now we'd like to formulate this as a vertex model. So we're going to take k copies of our previous vertex model, we're going to superimpose them, and we're going to add some interaction weight. So our constraint is that if we want to use the same sort of arguments as before, we still need the Yang-Baxter equation to hold. And that's why we have these particular style of interactions. For some reason, for these interactions, you still have integrability. And our integrability is actually coming from a much more general vertex model of Agarwal, Borden, and Wheeler, where they were studying supersymmetric SL2, so SL2K. And they have some R matrix for this quantum group. And the weights we have come from degenerating this R matrix. So we kind of just inherit the Yang-Baxter equation from their more general vertex model. All right, but I'll briefly go through what the weights are. It's not really so important. They exist, they're Yang-Baxter integrable, and they match up with the domino weights I gave before. But I'll try to highlight some of the features. So recall that our purple weights took this form for a single color, where we had an X if they exit right. Now for our K different colors of paths, the weight is just going to be you're going to look at each color of path. They're going to have the same weights, except instead of X, you're going to have X times T to some power, where this power depends on the larger colors in the model. So it's sort of a product over each color, except this parameter X changes depending on what else is present at the face. Okay, and then in this case, it imposes the same interlacing conditions that in the purple rows, that the partitions, every partition in the tuple, or the partitions of each like index must co-interlace. We'll get this X to the number of boxes you need to add to the diagrams, and then along with some T interaction, which turns out to be something that maps to those domino interactions I said before. And the gray weights are slightly more complicated. But the point is, in the end, you'll get exactly the weights from the dominoes, the exact same interlacing conditions, and then some overall factors that only depend on the rank, and we'll just throw them out later. And again, it's Yang-Baxter integrable, where now this the weight that's important to us is going to be this 1 over 1 plus xy times t to some power, where the power depends on the color, how the other colors in a face are behaving. So we have this theorem where the partition function for this vertex model, where now we have k colors of paths with the weights I described before, is going to be equal to some overall factor that we ignore times the partition function of the k-tilings of the Aztec diamond. And in particular, you compute the partition function for the k-tilings of the Aztec diamond, and it has still a nice product form that looks very similar to the product form for the one tiling, except now we have a product over the number of colors and this t parameter here. Yeah. Yeah, here? Oh. Okay, and the proof of this follows more or less exactly the same way as what we had before. We have some bijection going through these interlacing sequences of partitions between the vertex model and the tilings. And then the Yang-Baxter equation lets us reorder the rows until they are ordered in such a way that it's simple to compute the partition function. And then the product comes from the cross weights that we needed to add to permute the rows. Okay, so basically exactly the same as the one color, except with more complicated weights. Okay, so this is our partition function for our k-tilings. So if you plug in t equals 1, we get just k, or the partition function for the single color Aztec diamond multiplied together k times, which sort of makes sense because at t equals 1, there's no interaction. But maybe surprisingly, at t is equal to 0, the only terms in this product that aren't 1 will be the ones where L was equal to 0. So in fact, we get exactly the partition function for the standard Aztec diamond. So somehow when t is equal to 0, the k-tiling degenerates into one tiling. And we have a bijective proof of this, which I'll now describe. And it's somehow easier to go through Schroeder paths than the other formulations I've given so far. So we need one further formulation of the Aztec diamond in terms of Schroeder paths. So here now we're going to assign a path segment to each domino. And this gives us a bijection between domino tilings of the Aztec diamond and these sort of some non-intersecting paths that either go horizontally or diagonally up or down. So for rank 2, these are all possible Schroeder paths. and all the tilings associated to them. Okay. And now if we translate our interaction weights to weights on these Schroeder pads, what we see is this, that whenever a larger and a smaller color meet, and the smaller color is above, you get a T. So that's these three. And then also when both paths go up diagonally, you get a T. So this is our interaction in terms of the Schroeder pads. So we can say, take these two domino tilings, we can draw them as their Schroeder pads, we can superimpose them, and we'll get something that looks like this. And these two dominoes become this look like this locally in terms of the Schroeder pads. And this is exactly the smaller color and the larger color meet with the smaller color on top. So this would contribute a interaction. This contributes a T. Okay, and so we're going to number these pads 1 to the rank, where 1 is the topmost, 2 is the second topmost, and so on. Okay. So now taking T to 0 really restricts what these pads are allowed to do. So let's just look at the topmost path where it starts. Now both the pads, so we're just going to focus on two colors. So if both paths went up diagonally, then we would get a power of T. So this is not allowed. So they both can't go up diagonally. So now suppose the blue path goes up diagonally. Well, then if the red path went horizontally, that means the blue path is above the red path. And eventually they'll have to meet since they end at the same point. So where they meet will contribute a power of T. So this is also not allowed. So we can see that when T is equal to 0, the blue path is forced to go horizontally because we just went through all the cases where it went up diagonally and those are not allowed. So the blue path is actually frozen and forced to go horizontally when T is equal to 0. Now you can do a same sort of argument for all the other paths, and you see that you'll end up with this section of frozen paths in this bottom left corner of our Aztec diamond. So when T is equal to 0, it introduces a large region of completely forced paths. And you can actually show that the blue path, the ith blue path will be squished between the ith red path and the I plus first red path. So this lets us have or construct a bijection between, say, 2 tilings of the Aztec diamond at T is equal to 0 and 1 tilings by, say, taking a configuration, deleting all the frozen paths near the start. So there's a whole region where paths were completely forced. We delete those. And then we take what's left and we just slide it diagonally down and left. And this gives us a configuration of a 1 tiling of the Aztec diamond. So with this bijection, we can actually compute the Arctic curve for the 2 tilings, or I guess the k-tilings, when T is equal to 0. So we know that the Arctic curve for the 1 color Aztec diamond is just a circle. So if we follow through this bijection, sort of in reverse, we can map what happens to the different components of the Arctic curve. And you end up with some piecewise ellipses. So ellipses in each segment that get glued together. And it's the same for all the colors. And we can look at a picture and we see that, you know, what we computed matches pretty well with the simulations. And in principle, you could do this for the full limit shape because the bijection tells you how all the paths move. You could keep track of everything that was happening and compute the height function for the 2 tiling. Okay. And we also have some, we can prove bijectively some results about swapping T and 1/T. There's just some geometric results where if you look at a tiling with interaction T, if you reflect it across the line y is equal to x, it'll give you a bijection with tilings, an interaction weight 1/t. So there's some sort of symmetry in the model with respect to inverting T and doing some geometric transformation to the tilings. But like I said before, for other values of T outside of 1, 0, and infinity, we really don't know what to say or what tools to use to study these things. For the single tiling, you can use all these machinery of Schur process and all the determinantal structure related to these Schur processes. But for with an interaction, it doesn't seem like that stuff still works. But it would be interesting to like sort of understand the asymptotic behavior of these tilings with interaction. Okay, and just another thing to note, the domino shuffle algorithm, if you're familiar with that, carries over very nicely to these k-tilings. It's how I made those simulations. It works almost exactly the same. So there are a lot of things in this model that generalize nicely what is already known about the usual Aztec diamond. And it'd be nice to be able to see what more we can get. Okay, I think that's my talk. Thank you.
Questions?
Actually, I have an obvious question just on the technique. I mean, with this technique, I mean, you seem to be able to get nice limit shapes. I mean, that's great.
Mhm.
And another question is, you know, at least in principle, is this technique applicable or strong enough to say something about shape fluctuations?
So it's sort of, I don't think so. It's sort of equivalent to like the Cauchy identity for Schur polynomials or for a symmetric polynomial. But usually to actually say something about the fluctuations, you need like more control than that. So I don't think, we need more tools to be able to say something stronger.
Thank you for a very nice talk. Maybe I misunderstood something. You said that you have not a clear understanding of this breaking of the reflection symmetry, or it's, I mean, it seems to me like quite obvious that when you introduce non-trivial T, you have these non-symmetric shapes.
So I guess what we don't have a good understanding of is why for the two different colors, it looks the same. It's not symmetric in terms of the colors. It depends on like smaller colors and larger colors.
Yes, but if you have symmetry between T and 1/T, maybe this is the answer. No, maybe not. Only when you have two. Only when you have two copies, maybe this symmetry can help. In general, it's not clear. All right. Okay, thank you.
Yeah.
Okay, more questions? Maybe I can ask a question. There is in the paper of Bardina Garwal-Willer, they play the game of expanding LLTs and Schurs in some way.
Mm-hmm.
Can you understand this here somehow?
I haven't tried. Probably, I'm not really sure. I don't remember exactly what they do.
But you can draw parallels between their work and yours, right?
Yeah, so it should be, so all the vertex models I drew here are degenerations of theirs. So probably a lot of the games they play should, you know, one could check how they degenerate to the vertex models I described, but I haven't done it.
Okay.
So my question is about the symmetry. So you said you don't understand the symmetry. Does this asymptotic sort of equivalence between colors suggest some sort of bijective correspondence? I don't know how to formulate this question, but maybe there is a bijection between the two sides at the discrete level, or do you think it's something that only emerges in the limit?
So I'm not okay. I don't know how it exactly works for the domino tilings, but for the LLT polynomials, it's not. So in this case, like each color corresponds to like one of our partitions, right? And for the LLT polynomials, it's not true that you can swap the partitions and get the same LLT polynomial back. So the symmetry doesn't hold at the level of symmetric polynomials, not in general. So the domino tilings are slightly different. There's some big product of the LLT polynomials. So maybe here, the differences cancel out and what you said is true, but I'm not 100% sure.